Welcome to Numerical Methods for Scientists and Engineers. Direct solution of systems of linear equations. Naive Gauss elimination and Gauss-Jordan methods. A typical linear system of equations with n unknowns has the following form. Engineers and scientists frequently encounter linear systems of equations in a variety of fields and applications where exact solutions of problems may be difficult or impossible to obtain analytically. This lecture focuses on the direct solution methods, Gauss elimination and Gauss-Jordan. Every linear system of equations can be expressed in matrix equation form, such as AX equals B. Matrix forms are required in Gauss elimination and Gauss-Jordan methods. Then the augmented matrix for this system is set up as follows. The augmented matrix, which is an n by n plus 1 rectangular matrix, is a compact way of representing a system of linear equations. It combines the coefficient matrix and the right-hand side of the equations into a single matrix. Gauss elimination is a method for solving a system of linear equations by transforming the augmented matrix into an upper triangular form, or row echelon form, through a sequence of row operations. And then performing back substitution to find the solution. In this video, we will describe the naive Gauss elimination method, which is the basic implementation of the elimination methods. The algorithm involving pivoting is an enhanced version of the Gauss elimination method and incorporates pivoting to improve the numerical stability of the algorithm, and it is covered in video 5. On the other hand, the Gauss-Jordan elimination method is an extension of the Gauss elimination method, which transforms the augmented matrix of a system into its reduced row echelon form, which allows for direct reading of the solutions to the system. The process of transforming an augmented matrix into an upper triangular form is called forward elimination. This process eliminates, or zeroes out, the elements below the diagonal elements, that is, the pivots in the augmented matrix. In this algorithm, we normalize or scale the pivots to 1. Although this is not strictly necessary in Gauss elimination, it does offer several benefits, such as reducing round-off errors and numerical instabilities and simplifying hand calculations. We begin by normalizing the first row by scaling it with 1 over A11, so that the pivot is 1. Here, presetting 1 over A11 to val eliminates retrieval and arithmetic inversion of the same quantity many times, thereby reducing CPU time. Here, the symbols used for matrix entries imply that the entries are filled, and they do not refer to numerical values. Next, using the first row, we eliminate the elements below the pivot, i.e., from rows 2 through n, by using presented row operations. This process eliminates the unknown x1 from all rows below it. In the meantime, as a result of row operations, coefficients in the matrix below the first row are modified. Prime notation, as well as newer symbols, is used to indicate that the rows have been altered. Here, AI1, which is to be accessed many times, is set to a new variable s in order to reduce retrieval and thus the CPU time. Moving to the second row, we normalize it by scaling it with 1 over A22, so that the pivot is 1. Likewise, val is set to 1 over A22. We apply the elimination process to all rows below the pivot, from rows 3 through n, which eliminates x2 from all the rows below it. We move on to the third row to normalize it by scaling with 1 over A33, and val is set to 1 over A33. In the subsequent arithmetic operations, val is used to save CPU time. Using the row operation given, we apply elimination process to all rows below the pivot, from rows 4 through n, which eliminates x3 from all the rows below it. We continue this process for all columns from the first to the row n-1. At the jth pivot row, the superscript j in parentheses indicates that this row has been altered j times. The rows above have already been computed. The rows below the pivot are yet to be updated. The normalization and elimination procedures are given by the following expressions. By the end of this process, the augmented matrix will be an upper triangular form, with all the elements below the diagonal being 0. The right-hand side vector also goes through n-1 modifications, which is denoted by B'. The circle symbol represents entries filled with non-zero numbers, though some may turn out to be 0. Now let us consider a system of 4 equations and 4 unknowns. This system can be expressed in matrix form as follows. The augmented matrix is set up as, with the coefficient matrix A on left and the right-hand side vector on the right side. The augmented matrix is transformed to Ux equals B', where U is an upper triangular matrix. Or U can be made into an upper triangular matrix whose diagonals are all 1s. Now let us consider a numerical example involving a 4 by 4 system given in the matrix form as follows. First, the augmented matrix, 4 by 5 in size, is set up. The goal of the first pass is to scale to create 1 as the pivot and eliminate the elements below it. We note that the first row, first column element is already 1, so there is no need for normalization. To eliminate the second row element below the pivot, we add -3 times row 1 to row 2. The resulting row is used to replace row 2. Next, to eliminate the third row element, we add 2 times row 1 to row 3. And row 3 is replaced by the resulting row. Then, we add -2 times row 1 to row 4 to eliminate the fourth row element. Row 4 is replaced by the resulting row. This also marks the end of the first pass. The goal of the second pass is to scale the second row to create 1 as the pivot and eliminate all the elements below the pivot. Again, we notice that the second row second column element is 1, and there is no need for normalization of the second row. Such decisions are limited to hand calculations and are not adapted to general Gauss elimination codes. To eliminate 5 in the third row, we add -5 times row 2 to row 3. And row 3 is replaced by the resulting row. To eliminate 1 in the fourth row, we add -1 times row 2 to row 4. We replace row 4 with the resulting new row. This operation also marks the end of the second pass. The goal of the third pass is to scale the third row to create 1 as the pivot and eliminate the element below it. Normally, the naive Gauss elimination algorithm requires normalizing the third row by multiplying it with 1/17. However, to avoid dealing with rational numbers, we will add minus 4 times row 4 to row 3 to create the pivot as 1. This would normally not be done in computerized algorithms. The new row, with the pivot as 1, replaces the third row. Now, to eliminate 4 below the pivot, we multiply row 3 by minus 4 and add it to row 4. Then, the row 4 is replaced with the resulting row operation. This also marks the end of the third pass. The goal of the fourth pass is to normalize the last row. The last row pivot is minus 9. Hence, scaling this row with minus 1 over 9, we complete the forward elimination procedure. The result is an upper triangular system of linear equations in augmented matrix form. The last equation contains only one variable, x4, whose solution is evident. x4 is 3. This solution is applied to the rest of the equations. The third equation now is an equation with x3 as the only unknown. Solving this gives 4, which is also applied to the other equations. We note that the only unknown in the second equation is x2, whose solution yields minus 1. Finally, the first equation is solved for x1 that gives 2. The Gauss elimination procedure ends here. The Gauss-Jordan method does not apply back substitution. Instead, the augmented matrix of the system is transformed into reduced row echelon form. Once the transformation is completed, the right-hand side becomes the solution vector. Setting the pivots to 1 during the forward elimination procedure becomes handy in the subsequent elimination steps. The goal of the fifth pass is to zero out the element above the second column pivot. This is achieved by adding minus 2 times row 2 to row 1. Then the resulting row is used to replace row 1. The goal of the sixth pass is to zero out the 2 elements above the third column pivot. To eliminate 10 in the first row, we add minus 10 times row 3 to row 1, which eliminates the third element of row 1. This row replaces row 1. To eliminate minus 3 in row 2, we add 3 times row 3 to row 2. We replace the second row with the resulting row, which marks the end of sixth pass. The goal of the seventh pass is to eliminate all the elements above the pivot in the last column. We begin by eliminating the 1 in the third row by adding minus row 4 to row 3. The resulting row operation replaces row 3. To eliminate 7 in row 2, we add minus 7 times row 4 to row 2. The row 2 is replaced with the resulting row operation. Finally, The last row is multiplied with 21 and added to row 1, which eliminates the minus 21 in this row. And, lastly, the row operation is saved on the first row. Notice that on the left side of the augmented matrix, we have created the identity matrix, and we can directly read off the solution of the linear system from the last column of the augmented matrix. In this video, first we obtain the solution of the linear system through the Gauss elimination and then continue to illustrate the Gauss-Jordan method. However, a code that finds the solution of a linear system with the Gauss-Jordan method is similar to the order followed in finding the inverse of the matrix. That is, we create the identity matrix column by column, as illustrated in 4 passes. That is all for now. See you next time with another topic. Bye.